Okay, so now we're on part 4 where we're going to talk about how nonlinearities could affect volumes of distribution. Okay, so as you remember, distribution is all about binding. So alpha-1 acid glycoprotein, AAG, and albumin both can have nonlinearities, and both can be saturated, if you want to think of it that way, and overwhelmed. We see nonlinearities with a drug called disopyramide, which is an antiarrhythmic, 1C antiarrhythmic, I think, no, 1A, I'm sorry, class antiarrhythmic. And you also can see albumin overwhelmed by valproic acid in the therapeutic range, all of these in the therapeutic range, and naproxen is another example of that. If you have nonlinear fraction unbound in plasma, if you think about those plasma binding sites as being overwhelmed, the fraction unbound is going to increase, so this is going to increase with increasing concentration, which would then in turn increase your volume of distribution at steady state as you have nonlinear plasma protein binding. If you have nonlinear tissue protein binding, again, you're going to overwhelm the system and there's going to be a higher free fraction in the tissue. That's more of it free in the tissues, which will actually decrease the volume of distribution, and therefore you would see a decrease in volume of distribution with increasing concentration. All right, now let's go over clearance. So nonlinear clearance. We've talked about most of these issues already, but we can give you some examples. So if you overwhelm the enzymes, the hepatic enzymes, hepatic clearance will become nonlinear. Some examples of this are alcohol. You've probably heard of zero order pharmacokinetics with alcohol, meaning ethanol. Phenytoin, which we've talked about, was kind of probably the most famous clinically important nonlinear clearance with hepatic enzymes, is phenytoin, and also salicylates. So these all happen in the therapeutic range of these drugs. You also can have, again, overwhelm the binding sites with salicylates, which would actually end up increasing clearance, hepatic clearance, right? So we can have nonlinear hepatic clearance. If we have nonlinear intrinsic clearance, if we go back and think about this for low extraction drugs, as concentration increases, the intrinsic clearance will decrease, as will clearance of low extraction drugs. If you have nonlinear binding in the plasma, the fraction unbound is going to increase with increasing concentration, and therefore the clearance will increase with increasing concentration of a low extraction drug cleared by the liver. Renal clearance. We have filtration, reabsorption, and secretion. Remember, filtration is GFR times fraction unbound. So if we have nonlinear binding, this fraction unbound is going to increase with increasing concentrations. So disopyramide will have an increase in the filtration clearance in the therapeutic range due to nonlinear binding. Also, we know active reabsorption is very unusual. Usually we talk about passive reabsorption happening in the distal tubule. There are some things that are actively reabsorbed, like vitamins and minerals. So ascorbic acid, which is vitamin C, is an example of this. So this can undergo nonlinear, it can be overwhelmed, so those active reabsorption sites can be overwhelmed. Therefore, the ascorbic acid will stay in the tubule more than it would, so you'll actually see clearance increase. Don't worry about this too much. It's not really clinically that important. However, active secretion, having nonlinear active secretion, is pretty common and should be recognized. So if you overwhelm those carrier sites that take the drug from the blood into the urine, the drug is going to, more of it's going to stay in the blood and not get that ride over into the urine, which will decrease the clearance. So this happens with penicillin and procainamide in the therapeutic range, because again you have this Michaelis-Menten property. Okay, I'm not going to go over that too much. I think that's the major point there. All right, that's the end of this section.